Thank you very much for the invitation of the organizers. So this talk is based on a joint work with just Sasha Bifidov, who just gave a fantastic talk. So we will talk about also determinant point process related to entire function. So let me first recall some basic definition from Bergman space, which means the holomorphic function. So I will first only focus on the open unit disk case. So we consider the holomorphic function on the open unit disk, which is square integrable with respect to the Lebesgue measure. So we collect all these functions. It turns out this is help space. So a subset of the unit disk will be called Bergman, will be called a uniqueness set for this Bergman space if any function from this function space can be determined uniquely by its restriction to this subset. For instance, if X contains an accumulation point, then of course it's a uniqueness. But in general, we will consider subset without accumulation points inside the disk. Okay, so the point process we are going to talk about will be the realization of the following random object. So we consider the very simple random series. So this is a formal infinite series. So we just take the coefficient to be identically independent distributed Gaussian random variables, complex. So then it can be easily verified that this series has radius convergence 1. So indeed, this formal series defines holomorphic function on the open unit disk. So this will be a random holomorphic function on the open unit disk. So we can talk about its zero set. So in a joint work with Bifidov and Shamov, we prove that in fact the zero set. So by this notation, I mean the set of zeros of this holomorphic function. So this random subset of the unit disk turns out to be a uniqueness set of our Bergman space. Okay, so let us briefly see how this result is proved. In fact, it is well known that the Bergman spaces are reproducing kernel help space with this well-known reproducing kernel called Bergman kernel. And it has been now a standard result that the zero set of our random Gaussian function on the unit disk is a determinant point process. So in fact, I think Sasha just gave the definition of determinant point process. So here we just recall that the definition is the following. So we have this, on the left-hand side, this is the nth correlation function. So it's given explicitly by the determinant of this n times n matrix. So, and in fact, this theorem proved with Bifidov and Shamov for the uniqueness fact is a corollary of this very general result. So in fact, for all point process satisfying this kind of correlation functions, we have uniqueness result. So, okay, so this is only our starting point of this work. The main point of this talk is the following. So, because by the previous result, we know that any Bergman function, square integrable and holomorphic function on the unit disk is uniquely determined by its restriction on our realization of a fixed subset of unit disk. So the natural question is how to recover a function from this function space from the data that the restriction of this function on this discrete subset. So in fact, this kind of problem was very well studied in the theory of interpolation sampling. So we just briefly recall what is the sampling set. So sampling set for Bergman space, meaning that we have, so this is a countable subset. So in this discrete weighted sum is bounded from both sides by the L2 now of this Bergman function. So for such subset is called sampling. For this sampling set, the reconstruction is sort of explicit. So we have this very explicit, kind of explicit formula. So the only non-explicit data is this holomorphic function, which is not direct if we are given just a general sampling subset. Unfortunately, in our setting, this zero set of random Gaussian function almost surely is not sampling. So it's not sampling, it's only uniqueness. So this standard theory cannot be applied here. So, but in fact, we can do in this setting. So the way how we reconstruct function is the following. So we first do the reconstruction for a fixed Bergman function and a fixed point. So in this work, we should consider the unit disk as the hyperbolic space. So the Poincare-Lobachevsky unit disk. So we recall the hyperbolic metric defined as follows. So we are able to prove that, in fact, for any Bergman function and any fixed z and parameter s, we have the following convergence, the convergent series. So let us see what is happening here. So here, fx, x is inside this random subset. So the right-hand side depends, of course, only on the values of our function restrict on this function. And in fact, there's some tricky part here. So this double summation is indeed needed. So because this function, you see here means we fix z and we consider the annulus around z. So around this point. So we do the weighted summation will have cancellation on these annuli, and after this cancellation, then we take the summation over the annuli, then it will be summable. If not, if we just take direct the sum over all x from this subset, in fact, we are not able to show the convergence, and it's unknown to us now. And then using this lemma, we can define this quantity. So this is just weighted summation, weighted kind of weighted average of our values on this subset. So then we prove that when our parameter approaches the critical parameter, we can recover our function at the point Z, the point Z. You see that this Z is not necessarily in this Z is just arbitrary Z, arbitrary point on the unit disk. So we recover the value of f at this point from the value of f on this subset. And in fact, this result turns out to be, we find the necessary and sufficient condition for this convergence. So the convergence, in fact, we can do a little better than Bergman function. So we only need some tempered growth condition on the holomorphic function. And in fact, the holomorphicity can be replaced by harmonicity. However, this does not mean that our uniqueness condition is improved, because here we are proving everything for a fixed function. It's not for all functions. So the natural question is whether this construction can be extended simultaneously for all function f. So in fact, we prove that in general, this is not possible by the following results. In fact, we can replace even this weight by more general weight, this exponential weight, by this kind of some more abstract setting. And in this very quite general setting, we can prove that the uniformly, if we take the supremum of the unit ball of the Bergman space, then this quantity in average has a lower bound, which is explicit lower bound. So this means that using even we change this weight, we cannot obtain zero. So here, what we are doing here is just this parameter S means we are going, we are optimize our variance from the set of this class of weights. So in more general weight, the supremum case cannot be go to zero. So we are not able to prove the simultaneous reconstruction for all function f. But however, this is not the end of the story. Because although we cannot reconstruct all function, we can still reconstruct simultaneously smaller subspace. So this is the result. Instead of considering the function which is L2 with respect to the big measure, we consider the L2 function with respect to some weight. But this weight goes quite fast. And this is, we find an explicit critical weight. Once the a given weight goes faster than this critical weight, then we are able to prove that the convergence. So here, here I denote the unit ball of this weighted Bergman space by this notation, and in fact, this uniform convergence holds for this weighted Bergman space with supercritical weight. And in fact, we say this is critical weight because indeed it's critical since the same result fails for the critical weight itself. So as a corollary, of course, from this we obtain the following almost sure convergence. But this convergence from this theorem to the corollary is Borel-Cantelli lemma. So we have to convergence have to go along a subsequence of the parameter, and these points inside the disk can only be extended to dense subset. But in fact, for another space we call a weighted harmonic Hardy space, meaning that we consider a fixed Borel probability measure on the unit circle, and we take function which is square integrable with respect to this Borel probability measure, and we then take the harmonic extension or the Poisson convolution of this measure on the unit circle. Then we get class of harmonic function on the unit disk. And for this space, we are able to prove that, in fact, we have the following convergence, and we can compare the two convergence. This convergence is for Z for a certain fixed countable subset, and the parameter is certain fixed countable parameter. But here, the parameter, there's no restriction for the parameter. So we only need the parameter go to the critical one, and we have all function and all points inside D, and these codes simultaneously hold. And moreover, in this result, we do not have uniform, whether this convergence is uniform on Z or not is not known, but for this space, we are able to show that, in fact, the above convergence is uniform locally on Z and locally on the unit ball or any bounded subset of this help space. And in fact, I state all results in the unit disk because just for simplicity, all these results, at least everything can be extended to the complex unit ball, and several results can be extended to real hyperbolic space, and also several results can be extended to quaternion hyperbolic spaces. I think that is all I want to talk.
Comment that Yanqi, but this is not entire functions.
This is harmonic function, but entire function.
Not entire. So in fact, there is this precisely is the difference, right?
Yes, indeed, I said this is a harmonic function, but since I noticed your title, so I'm just mentioning that it's the entire function.
Which they're not, in fact. So it's different.
In fact, yeah, yes, you are right.